Hi everyone and welcome to this presentation. First of all, let me thank you for being here. Let me introduce myself. I am AINAOUI from Faculty of Science, ACHOUBY University in Morocco. So as you can see on the slide, the topic of my presentation is about analysis of simultaneous effects of temperature and irradiance on PV metrics and model physical parameters of a PV solar module operating under nonstandard conditions. So this work was done at the laboratory of instrumentation of measure and control. Now let's start by looking at the outline of this presentation. I start off by introduction, then I move on to the fundamental equations of single-tide model. After that, I go on the main parts of this work, which is about simultaneous effects of MBST temperature and POAI irradiance on PV metrics and model physical parameters. Then I will show you the results, and finally we have the conclusion. Now I'm going to start by introduction. So as you know, various factors can influence the performance of photovoltaic solar modules, including temperature and irradiance. The problem addressing this work is the study of simultaneous effects of back-surface temperature and plane-of-array irradiance on PV metrics and model physical parameters of photovoltaic solar modules. The efficiency of photovoltaic solar modules operating under non-standard conditions or outdoor under arbitrary conditions is strongly dependent on POAI irradiance and MBST temperature. Then it's very important to be able to determine model physical parameters with precision for any values of irradiance and temperature, for generating current voltage characteristics and predicting behaviors of photovoltaic solar modules. Now let's turn to the next part of my talk, which is about modeling. So for modeling a PV cell or a PV module, we can use the single diode model, also known as the 5-parameter model. The equivalent circuit for this model is given in this figure. If we look here, we can see a source of photocurrent, a diode, a shunt resistance, and a series resistance. So the main expressions describing single diode model is written like this. Let's move now to the fundamental equations of single diode model. It is the characteristic equation connecting output current to output voltage and 5 physical parameters. From this equation, we can write the characteristic equations at key point of current or current voltage characteristics. So here is equation at open circuit voltage point, equation at short circuit current point, and equations at maximum power point. As I pointed out in the introduction, the efficiency of a PV solar module is strongly dependent on temperature and irradiance. So to know effects of MBST temperature and POAI irradiance on PV modules, we need first to determine 5 parameter model values. For that, we have used the new method of solution called additive factor variation for the transcendental equation method, developed in our laboratory. This method is based on transcendental equationing the series resistance to additive factor. First, we give the expression of saturation current, then the expression of the photocurrent, and the expression of maximum power current, then the expression of polarity conductance, and finally we establish the transcendental equation in the series resistance to the additive factor and to PV metrics corresponding to the key point of IV characteristic. Turning our attention now to this algorithm that summarizes the additive factor variation for a transcendental equation method for extraction model physical parameters values as standard test condition. For this method, we use additive factor as a variational parameter. We assign an initial value to additive factor and resolve equation 11 via MAP software to obtain the values of RS and calculate values of GP, IPH, and IS using successively equation 9, 7, and 6. Then we vary additive factor with a step to minimize LMSO and maximize R square. For describing effects of temperature MBS and irradiance POAI on open circuit voltage, we choose this model. So for short circuit current, we consider that IAC varies linearly with temperature and irradiance. To describe variation of peak power point current and voltage versus MBS temperature and POAI irradiance, we use these mathematical models. So to calculate IPH, we use the mathematical models of photocurrent, and for calculating IS, we use the expression of saturation current. Equation 18, equation 19, and equation 20 make a system of three nonlinear equations with the unknown functions. They are the foundation of the numerical procedure aiming to determine variation of adjective factor, series resistance, and parallel conductance with regard to MBS temperature and POAI irradiance. And here is the algorithm that summarizes the numerical procedure for determining the values of the 5 model physical parameters for arbitrary values of MBS temperature and POAI irradiance. We vary MBS temperature and POAI irradiance, then we calculate APH via equation 16 to determine variation of adjective factor, series resistance, and parallel conductance versus MBS temperature and POAI irradiance. We use Mapper software to resolve numerically the system of nonlinear equations. After that, we deduce the value of saturation current using equation 17, and finally we generate current voltage characteristics. And for testing numerical methods presented, we use Jinko Solar module. So here is characteristics of Jinko Solar module operating under standard test conditions. Next, to find the values of temperature and irradiance coefficient, we achieve two-dimensional fitting to experimental values of open circuit voltage, short circuit current, and maximum power voltage and current under arbitrary values of MBS temperature and POAI irradiance. Now let's look at the next slide, which shows the results. So in this table we present the 5 physical parameters of Jinko Solar module obtained via our proposed method at standard test condition. So here we plot current voltage experimental characteristics as well as optimized characteristics. So if we look here, we can see that the generated IV characteristics coincide with the measured characteristics. So this shows that the performance of our proposed numerical approach is very efficient. As you can see in these figures, we present optimized and experimental values of short circuit current, open circuit voltage, maximum power current, and maximum power voltage with multi-irradiance and multi-temperature. For MBS temperature vary from 15 to 75 degrees Celsius with a step of 5 degrees Celsius. We note that mathematical models give accurate values of PV matrix whatever the values of MBS temperature and POAI irradiance. And in these figures, we present two-dimensional variation of series resistance, parallel conductance, adjective factor, photocurrent, and saturation current as function of MBS temperature and POAI irradiance. So all these figures, POAI irradiance varies from 100 watts per meter square to 1100 watts per meter square, and MBS temperature varies from 15 to 75 degrees Celsius. We can conclude that for a PV solar module operating under nonstandard conditions, the model physical parameters are very sensitive to variation of MBS temperature and POAI irradiance. I'd like now to end with a summary of the main points. In this study, we focused on modeling variation of cardinal points of photovoltaic solar modules operating outdoor under arbitrary conditions versus MBS temperature and POAI irradiance. We investigated simultaneous effects of MBS temperature and POAI irradiance on PV metrics and model physical parameters. We noticed that the numerical values of model physical parameters gave generated characteristics identical to experimental characteristics. We can conclude that the mathematical models describe well the variation of cardinal points as function of MBS temperature and POAI irradiance. For arbitrary values of MBS temperature and POAI irradiance, the numerical method for extracting the values of the model physical parameters is very efficient. So, many thanks for your attention.